welcome to this lesson, grade 11s, where we are going to be looking at Euclidean geometry. Remember, in Euclidean geometry, that's where we use theorems and we prove certain things that we are asked to prove by using logic and reasoning. Okay, so what we're going to do today is we're going to go over what you should know, what theorems you should know in order to write the exam. I'm simply going to go over the theorems that you need to learn, the converses, which theorems you need to prove, and also just give you a few hints and tips of how to answer certain questions using the theorems. All right, so what should you know from before? Of course, everything that you've learned so far from grade 9 is assumed. So we're talking about angles on the straight line. We call them axioms. It's things that you don't have to prove, but things you are expected to know. So angles on a straight line, parallelogram theorem, properties, all of those kind of things you need to remember. That kind of information will not be given to you, okay? We need to accept all of those results from earlier grades as what we call axioms. And remember, importantly, no marks are awarded for statements that do not lead to solving the problem. Now, what this means is, say that you've got a diagram and you can clearly see that there are two angles in a triangle that are equal to each other because they are base angles of an isosceles triangle. But that has absolutely nothing to do with finding the value of, say, x, which you've been asked to find. So even if you write down the two equal angles, if they have nothing to do with the solution that you need to find the answer to, you will not get marks for that. So do not just write down any information that you can see and hope to get marks. You will not. Okay. What you also need to remember, a theorem from grade 10, we call it the midpoint theorem. It tells us that the line joining the midpoints of two sides of a triangle, so there we have D and E, two sides of a triangle. The line that joins them, DE, is parallel to the third side of the triangle and a half the length of the third side. So DE would be a half of BC. You need to assume this result. You will not be asked to prove this result, but you need to know this as it can be asked in other questions. All right. So what is a theorem and what is a converse? Well, a converse of a theorem is a statement that is formed by interchanging what is given in a theorem and what is to be proved. So for example, the theorem might be the opposite angles of a parallelogram are equal, okay? So the opposite angles are equal of a parallelogram, that's the theorem. The converse would be if the opposite angles of a quadrilateral are equal, then the quadrilateral is a parallelogram. So we interchange what is given and what is to be proved. All right. So in your grade 11 exam, you are expected to know how to prove certain theorems. You are not expected to know how to prove the converses. So the first theorem you need to know how to prove, we call it the line from center theorem, which says that the line drawn from the center of the circle perpendicular to a chord bisects the chord. So you can see in your diagram, if O is the center of a circle, if we've got a line that is perpendicular to the chord, let's call it AB, then that line from the center will bisect the chord such that if we call this point M, then AM is equal to MB. That theorem you need to know how to prove. The converse of the theorem now, and remember when you're stating a converse, you cannot assume anything from the actual theorem itself. So the converse says the perpendicular bisector of a chord passes through the center of the circle. So in other words, if you're given this diagram and you can see that this line is drawn perpendicular, the line from this point in the middle of the circle is drawn perpendicular to a chord, bisecting the chord, then it must mean that if I follow this line through, it will take me to the center of the circle. All right. Also, what's important is the way you write out your reasons. You have to use proper statements. So line from center, perpendicular to chord, and that kind of thing. It's important the way you list your reasons. Remember in geometry, whenever you answer questions, if you make a statement, there must be a reason that that statement is true. It's logic, right? So therefore, if you make a statement, AM is equal to MB, reason, line from center is perpendicular to chord. All right. So you need to remember to make the correct statements whenever you give a reason. All right. One of the other theorems you learn is angle at center, and what that tells us, and I'm going to show you some nice diagrams about this, it says that the angle subtended by an arc at the center of the circle is twice or it's double the size of the angle subtended by the same arc at the circle. At the circle means on the circumference. It's on the same side of the chord as the center. So this is what it's looking like. And you'll see you've got a nice animation there showing you that the angle can move around the circumference of the circle. So the angle at the center of the circle is twice the angle at the circumference of the circle. That's really what the theorem is saying to us, and you need to be able to prove it. Of course, there are three different types of diagrams, and as you can see in the animated one that's moving from side to side, how the angle on the circumference can actually change such that the angle at the center is twice the angle at the circumference. The one that many learners struggle to see is diagram 3, where the angle is actually this angle here, right, which is not, and if you look at the angle on the circumference, angle C, you look at that and you think, oh, but that doesn't quite look like what I'm used to. So normally we've got our arc, okay, or sometimes a chord, and we see that it subtends the same angle at the circumference and then an angle in the center, and so we identify that one quite easily, right? And we look at this diagram, the third diagram, and we say, okay, well, that doesn't look really like angle at center to me. How do I identify it? Well, you identify your arc as AB, that arc there, or if you want to draw your chord AB in, and you can see that AB subtends, in other words, makes an angle of O here at the center, and then it also subtends. So if we take AB and we continue it, we see that it makes an angle of C on the circumference. So this angle C is a half of that angle O. All right, so you can see there are three different diagrams that you will be expected to know to prove the angle at center theorem. All right. The next one is the angle in the semicircle. And now what this is, it's basically a deduction of angle at the center being twice the angle at the circumference. So in this one, your angle in the center actually measures 180 degrees. So have a look at the diagram. We say that the angle subtended by the diameter, which is BC, at the circumference of the circle is 90 degrees. So in other words, if I look at line BC and I subtend, so I make an angle on the circumference, that angle is going to be 90 degrees. And we often use this theorem, we call it angle in semicircle. So this is a direct deduction from angle at center. The reason being, this angle at the center is now 180 degrees. It's a straight line, right? So therefore, if I look at the diameter BC, or this chord, we see, this arc, we see that we have an angle formed on the circumference and an angle formed at the center. So therefore, if the angle at the center is 180 degrees and my theorem says the angle at the circumference is a half of that, well, what is a half of 180? It's 90 degrees. The converse of that angle in the semicircle says that if the angle subtended by a chord, so we don't know that BC is a diameter, but we can see that the angle subtended by the chord at the circumference is 90 degrees, so we can see that that's 90 degrees, then this chord here must actually be a diameter. All right. An important one that will come up later again when we talk about cyclic quads is angles in the same segment. This tells us that if angles are subtended by the same chord of the circle and they're on the same side, so they're both on this side of AB, then these two angles are equal. Your reason, when we give the reason, if we say, for example, D is equal to C, our reason will be angles in the same segment. Another one that follows on from that, which you aren't expected to prove, is equal chords subtend equal angles at the circumference and at the center. This is one we tend to forget, but it sometimes has important implications for the proof of whatever we are asked to prove in a question. So all it says is that if you've got two equal chords, so for example DC and BC, and they are equal to each other, then the angles that they subtend are going to be equal. So E will be equal to A. The same thing happens if you've got equal chords and they both subtend angles at the center, then O1 will be equal to O2. And the reason there will be equal chords. All right, let's talk about cyclic quads. Remember, in a cyclic quad, all 4 points of the quadrilateral touch the circumference of the circle. Sometimes you'll be asked to prove that a quadrilateral is cyclic using the reasons that we have from our theorems, but the quadrilateral itself may not be drawn inside a circle. But what it means is when we say prove that it's a cyclic quad, it means that you can actually draw a circle around those 4 points. It's not necessarily the circle that you've been given in your diagram, but you will be able to put another circle around those 4 points. This is a theorem you need to know how to prove. Opposite angles of a cyclic quadrilateral are supplementary. So if I have angle X and angle Y, and we know that A, B, C, D, what do we have here? We've got B, E, C, D. We can see 4 points touching the circumference. So that is a cyclic quad. So therefore, angle D plus angle E, or X plus Y, will be supplementary, which means it adds up to 180 degrees. The converse of this, which is what we will use to prove that a quadrilateral is cyclic, is that if we know that X plus Y, which are angles in a quadrilateral, if we know that those are in fact supplementary, so they do add up to 180, it means that the quadrilateral must be cyclic. All right, sticking with cyclic quads, we have that the exterior angle of a cyclic quad is equal to the opposite interior angle. So B2 will be equal to angle D. This is another one that we can use to prove that a quadrilateral is cyclic. The converse is exactly what we're saying. To prove that a quadrilateral is cyclic, if the exterior angle, so if we can prove that B2 is equal to D, then we can show that this quadrilateral is cyclic. Obviously, in that case, you won't be able to see directly that your points are lying on the circumference of the circle. It will be a quadrilateral somewhere within the circle, and you can show, using exterior angle of a cyclic quadrilateral, that quadrilateral is cyclic. All right, we'll recap this when we come back, but let's take a quick break for now. Well, hello again. So glad that you came back to join us as we continue talking about our circle theorems and remembering which ones are important that we need to prove in exams. So just before the break, we were looking at cyclic quadrilaterals. I want to remind you about the ways that we can prove a quadrilateral is cyclic. We can either prove that the opposite interior angles are supplementary. Therefore, if we can prove that there's a quadrilateral and the opposite angles here are supplementary, that means they add up to 180 degrees, then that quadrilateral might be cyclic. The other way, or will be cyclic, not might be cyclic. If we can also prove another reasoning, depending on what diagram you've been given, of course, that if you've got a diagram and you can prove that the exterior angle is equal to the opposite interior angle, then indeed that quadrilateral is also cyclic. Then the one we didn't mention explicitly, but it's certainly true and we use it often, is the converse of angles in the same segment. So let's go back to that diagram. So if we can show that angle D is equal to angle C, then in fact your quadrilateral ABCD will be cyclic. Remember, when you're trying to prove that a quadrilateral is cyclic, it is not always the case that all 4 points will be given to you as on the circle. So you've got to use any of those 3 reasons to show that the quadrilateral is cyclic. All right. One of the theorems that you actually need to assume, an axiom, so you need to remember this one, even though it's not given to you explicitly, we accept it as an axiom, so that means we accept it as truth and we don't question it, is that a tangent to a circle is perpendicular to the radius at the point of contact. So if we've got a tangent T and a circle centered O, then where the radius meets the tangent, the angle there is 90 degrees. That's what the theorem is saying to you. Tangent is perpendicular to radius, and that's the reason you would use as well. When you write this as a reason, you can abbreviate or shorten it to tan perpendicular to radius, or in fact, diameter, depending on what you've been given. The converse of this is if we have a line that is drawn perpendicular to the radius or the diameter at the point where the radius meets the circle, then that line is a tangent to the circle. So in other words, if you know that this is the center of the circle and you can see that this angle is given as 90 degrees, or you've proved that that angle is 90 degrees, then in fact the line that's drawn at point T is a tangent to the circle. All right, another theorem that we don't come across often, but again it's one of those that can be essential to the proof of a theorem, is that tangents drawn from a common point are equal. So two tangents drawn to a circle from the same point, very important this, they have to be drawn from the same point. If they're not drawn from the same point, you end up with completely incorrect reasoning. Tangents drawn from the same point outside a circle are equal in length. And obviously that then has a lot of implications for right angle triangles and that kind of thing. All right. Carrying on with tangents, and one that you do need to be able to prove is the tan-chord theorem. And it says that the angle between the tangent to a circle and the chord drawn from the point of contact, so basically this angle here, is equal to the angle in the alternate segment, which means it's the one opposite it. So it's not this angle B here. Don't make that mistake, please. It's not the angle in the same segment. It's in the angle in the alternate segment that the angle between the tangent and the chord is equal to. So the tan-chord theorem, so when we abbreviate our reasoning, we can say tan-chord theorem. All right. Now the converse of this is if we have a line that's drawn through the endpoint of a chord, making with the chord an angle equal to the angle. So in other words, basically if we look at what the converse says, if a line is drawn through the endpoint of a chord, making with the chord an angle equal to an angle in the alternate segment, then the line is a tangent to the circle. Basically all it says is if you can show that, or if somehow it is given that this angle is equal to that angle, then certainly this line SA must be a tangent. Okay, so that's all the converse really says to you. All right, guys, so I want to go through in detail now some of the reasons that you should be, well, all of the reasons really that you should be using for circles. And it's very, very important because obviously we see the diagrams. You use the diagrams to help to get to your logical endpoint, but often you do not make the correct statements when it comes to giving your reason. And remember, every statement in geometry has to be accompanied by a reason. Otherwise, it doesn't make sense. And also remember, like I said to you in the beginning, if there's something that is true in your diagram, but it does not actually lead to the answer you are looking for. So say, for example, we're looking at the tan-chord theorem, and I can already see, say, for example, that this line CA is a diameter. Just say, okay, obviously it's not because this line isn't, we don't know that where the circle center is. But let's say CA is a diameter. And I just have that this is 30 degrees, and therefore angle C, if I'm asked to prove, would also be 30 degrees. But then in stating that angle C is equal to angle A, I happen to also say AC is a diameter. You won't get any marks for saying that because it is irrelevant to your actual proof. So remember to only make statements that lead you to the final answer. All right, let's go through those reasons. Those reasons are important, and you will only get full marks for your reason if you state it correctly. All right. So the first one that we were talking about is that a tangent to a circle is perpendicular to the radius at the point of contact. We abbreviate that one to tan perpendicular to radius, or tan perpendicular to diameter if we've been given the diameter. All right. The converse of that is if a line is drawn perpendicular to a radius or a diameter at the point of contact, then the line is a tangent to the circle. That we can either say line perpendicular to radius, and in fact this wasn't the very first one we looked at. We looked at line from center. So this was, I think, the third or so, but I'm not going to hazard a guess there. It's the third or fourth one. If a line is drawn perpendicular to the radius, then basically what it's saying is where they meet, if that angle is 90 degrees, then that line must be a tangent to the circle. The reason you would use there, line perpendicular to radius, or the converse of the tan perpendicular to radius theorem. Okay, now this is the first one we started with, the one that you need to be able to prove. Is the line drawn from the center of the circle to the midpoint of a chord is perpendicular to the chord. So that's the theorem. How do we abbreviate that when we're writing down our reasons in geometry? We just say line from center to midpoint of chord. Okay? And part of that theorem says that the line drawn from the center of a circle perpendicular to the chord bisects the chord. So essentially it's the same theorem, just expanded on. So therefore we use the same reasoning, line from center perpendicular to chord. Okay, so it's just slightly worded slightly differently, but it's essentially the same theorem. And then we're going to look at the opposite of that, which says that the perpendicular bisector of a chord passes through the center of the circle. So that's our converse, and there our reason is perpendicular bisector of chord. The angle at center is twice angle at circumference. We did look at all the different 3 diagrams there. This is one that you need to be able to prove. So the angle subtended by an arc, it's quite a long theorem to have to state out in words. So you can simply abbreviate that to angle at center is equal to 2 times angle at circumference. And of course you can use those symbols to represent angle. All right. The angle subtended by a diameter at the circumference is 90 degrees. So in other words, this is angles in the semicircle. So you can in fact say angles in the semicircle. We do understand that that means angles. Or you can say diameter subtends right angle, or angle in half circle like that, which is what, if we try and read it, that's what it's saying, but it basically means angle in semicircle. If we look at the converse of that, we can simply say converse angles in the semicircle. All right, and we're coming to an end now of the correct reasonings we should use. If we have angles subtended by a chord being equal on the same side of the chord, that we know commonly as angles in the same segment, and that's an acceptable reasoning. We saw the other one where we saw that there was a line segment joining 2 points and subtending equal angles on the same side of the line segment, then those 4 points were being cyclic. So basically all that is telling you is that we've got that the 2 angles, they look like they're in the same segment, so it's the converse of angles in the same segment if you're using that to prove that a quadrilateral is cyclic. Another one that we saw when we were dealing with chords was that equal chords subtend equal angles at the circumference, so we just use the reason equal chords. Equal chords subtend equal angles at the center, again, equal chords. And this one we didn't really touch on, but this is one that you may come across. We don't use it often, but equal chords in equal circles subtend equal angles at the circumferences of the circles. So basically, if you have 2 circles, they are equal to each other, and you've got a chord, say, subtending an angle there, and you've got another chord subtending an angle there, and we know that these are equal circles, and you know that these chords are equal, then these 2 angles here would be equal. Not one that we use often, but that is equal circles, equal chords. The one that we didn't really touch about here is the cyclic quadrilateral ones, and of course we use the one exterior angle of cyclic quad, that's what we abbreviated to, and then opposite angles of a cyclic quad being supplementary. All right, guys, so we've covered a lot of theory in this lesson where we looked at the different types of reasons that you can use, we've looked at how to prove quadrilaterals are cyclic, and we've looked at all of the different theorems that you need to know for exam purposes. We need to obviously put all of this into practice, which we will do in a lesson at another time, because that's the important thing about geometry. It's not just the theory, it's about how we use that theory and that logic to get us to the point, the end point that we need when we are asked to prove geometry riders. All right, thank you so much for joining us again. We'll see you next time.